The Laplace inversion integrals that are needed are often not as simple as in section 1324. We illustrate this for our vibrating string of length and initially address in the horizontal equilibrium position subject to the following time-dependent boundary condition at 1 and x equals n. So we have partial differential equation. Second derivatives of u respect to t squared equals c squared. Second derivatives of u respect to x squared, that is 13.5.1. So we have initial condition u of x 0 equals 0. Derivative of u respect to t squared of x 0 equals 0. That is 13.5.3. So we have a boundary condition u of 0t equals 0 and u of lt equals t. So the third initial condition facilitating the use of the Laplace transform of u of t x t. So we have u more of x s equals integral of e to negative s u x t times dt. So this is 13.5.4. Then by transforming 13.5.1, so u bar of x s, so satisfies the ordinary differential equations of ordinary equations s squared u bar equals c squared, second derivative of u bar over respect to x squared. So this is 13.5. Then, where ds is the Laplace transform of dt, we can easily determine u bar of xs. So u bar of xs plus s since 9h of s over c x over sin h s over c over. So this is 13.556. So this is 13.5 over sin h times c over c s over c times l. So this is 13.5.8. The convolution theory implies that u of x t equals integral of t minus p naught f of t minus p naught times t p naught. So this is from 0 to 3, so this is 13.5.9. Then where f of t is the inverse Laplace transform of f of s. Sin h times s over c x over sin h times s over c times l. So this is 13.5/10. Where f of t is the inverse Laplace transform of f of s. F of x sin h times c over where f of t is the inverse Laplace transform of f of s equals sin h times s over cx over sin h times s over cl. So equals is to s over cx minus e is to negative s over cx over e is to s over cl minus e is to negative s over cl. Then we can put up this a is to s over cx minus e is to negative s over cx over e is to s over cl times 1 minus e is to negative 2s over c times n. Then we show that e is 2s over c times n times 1 minus negative E is the negative S over C times L. Then the E is the S over C L times 1 minus E is the negative 2S over C L equals E is 2S over C times L times 1 minus E is the negative 2 times S over C L. So equals E is to S over C L minus E is to S over C L. E is to negative 2 times S over C L. So equals E is to S over C L. Then S over CL minus 2 times S over CL equals negative S C over L. Minus E is to negative S over C L. However, due to the denominator, this cannot be analyzed in a simple way. Instead we can introduce as finite and infinite series of exponential based on the geometric series. So geometric series 1 over 1 minus x equals 1 plus x squared plus if absolute value of x is bigger than 1. So Fs equals open parentheses E is to S over C minus E is to negative S over C S over. So dapat natin siya i-integrate and E over is to S over C L times ma-integrate siya kay 1 over x is equal to x to negative 1. 1 minus E is to negative 2s over C L. So equals, then ano na siyang ma-integrate? It is the negative S over C L times E. E is to S over C L x minus E is to negative S over C x. Then 1 plus E is to negative 2s over C L plus E is to 2s C over L squared plus. So, ano mo na siya? Of infinity of n equals 0, E is to negative s times 2 n minus x plus l over c. Negative E is to minus Sn C is equal to D is to S over C x times E is to negative S over C f equals negative S over C x E is to negative S over C L is equal to negative S over C times E S over C x negative E is to negative S over C x. So this is the final result. E 0 x L. So E plus L plus X over C and B equals L minus X over C. Let's proceed to the wave equation and its wave function. The Laplace transform can be used to determine the relationship between solutions of homogeneous partial differential equations and its corresponding Green's function. Consider the wave equation on a finite interval x is greater than 0 is less than n with sources and time-dependent boundary conditions. So we have partial differential equation, second derivatives of u, respectively squared equals c squared, second derivatives of u, respectively x squared plus g of xt. So that is 13.6.1. So we have a boundary condition, u of 0t equals 8 times t. Then u times nt equals dt. That is 13.6.2. So we have a initial condition, u of x0 equals f of x. Then derivatives of u respectively of x0 equals g of x. That is 13.6.3. So Green's function, the Green's function of g, x, t, x naught, t naught satisfies second derivatives of g respectively squared equals c squared, second derivatives of g respectively x squared plus delta of x minus x naught times delta of t minus t naught. That this is 36.6.4. G of 0 t. So ako ang hindi ko g of 0 t x naught t naught equals 0. G of ht semicolon x naught t naught equals 0. So subject to the causality principle, g of x naught t naught equals 0 for t is less than t naught. Laplace transform of Green's function in the section, we determine the Green's function using the transform of 13.6.4 and 13.6.6 yan. So we have s squared g bar equals c squared, second derivatives of g bar over s squared, respect to x squared plus delta of x minus x naught times e is to negative s t naught. So this is a 13.6.8. Then g bar of 0 s semicolon x naught t naught equals 0. So this is 13.6.9. Then g bar of l s semicolon x naught t naught equals 0. So this is 13.6.9. Then we have g bar of x s t naught x naught t naught equals gamma sine s over c x is less than 0. Then we have gamma sine h c over s over c x naught sine h c of s over c. So l minus x times x is greater than x naught. So this is 13.6.11. Then we can obtain this if sine h times a plus b equals sine h a cos b plus cos A. A sine HB. In the preceding section, we showed 13.5.8 that 13. So we have u bar of x as equals b as sine h s over cx and sine h of s over c l. So this is 13.6.13. So here we will relate this to the Laplace transform to the Green's function 13.6.11 with 13.6.12. So 13.11, so g bar of x s semicolon x naught t naught equals e is the negative st naught sine h of s over c times n minus x naught sine h of s over cx over c squared sine h of s over cn. So this is 13.6.14. We note that x naught equals L and t naught equals 0. Then derivative of u bar respect to x naught of x d semicolon x naught t naught equals negative e is to negative s t naught cos h of s over c times n minus x naught sine h s over cx over c squared sine h of s over c l. Similar to the term appearing in 13.6.13, kani siya? Mao ni ang what? Uh, Derivative of g bar over x naught is of x and s l and 0. So negative sine h of s over c of x over c squared sine h of c over s over c of l. Then we have u bar of x as equals negative c squared bs derivative of g bar respect to x naught x t and minus t naught then and l 0 d t naught.